Hi and welcome back. In this video lecture we will give some design guidelines for model predictive control. Let's do a little revision. Let's go through the results that we stated in the previous video lecture. So there we stated the MPC stability assumptions. These are the regularity assumptions, attractivity assumptions, and lastly the terminal condition, TC. The terminal condition, which is a very important condition to remember, is that VF is a function that is non-negative valued. It is defined on XF. It's continuous. It is equal to 0 at 0. And, that's very important, VF is larger than or equal TVF for every X which is inside XF. So inside the terminal set we must have this condition that comes from dynamic programming. Note that this condition implies that XF is a control invariant set for the dynamical system. We stated that if we have these MPC stability assumptions, if they are satisfied, then the set of feasible states for the problem of horizon n is positive invariant, so the set Xn is positive invariant for the MPC controlled system. We said that the origin is globally attractive for the MPC controlled system over this set, the set Xn, and we also stated the performance bound and a couple of monotonicity conditions, namely that when you increase the prediction horizon you will obtain a lower optimal value, so Vn plus 1 star is less than or equal Vn star, and you may obtain a larger set of feasible states, so Xn plus 1 will be a superset or equal to Xn. We also said that if we have some additional conditions, some additional assumptions, the most important one of which is that XF must contain the origin in its interior, then we can have global asymptotic stability for the origin. The origin can be globally asymptotically stable for the MPC controlled system over the set Xn. In today's lecture we ask how exactly can we determine VF and XF to achieve attractivity and hopefully to achieve global asymptotic stability as well. We will start by focusing on constrained linear systems, and then we will move on to constrained nonlinear systems. So MPC for linear systems. Let's have a look again at the terminal condition. That's the most important condition to really have in mind. The condition states that VF is larger than or equal TVF. Now if we use the definition of T, TVF can be written out like that. It is the minimum with respect to U, which belongs to the set U uppercase, of L of x comma U plus VF evaluated at F of x comma U, and this condition must hold for every X in XF. Let me repeat again that this implies, and it would be good for you to try to prove this as an exercise, to see this as an exercise, that XF is a control invariant set for the system we're talking about. For xt plus 1 is f of xt comma ut, so that's a good exercise. Now let's make a few observations. This is TVF, but VF is the same thing as V0 star. V0 star just pertains to the dynamic programming procedure. It is TV0 star. Now if you apply T on V0 star, by definition you obtain V1 star. So the right hand side is V1 star. So another way to look at this inequality is that VF of x is larger than or equal V1 star. Now this V1 star, under the regularity assumptions, the minimum in the definition of V1 star is attained, and it is attained at kappa 1 star. Now kappa 1 star is a little difficult to compute. It may not be an easy thing to compute in general, especially for nonlinear systems. So the trick here is to realize that we don't really have to determine kappa 1 star to make sense of that inequality. What we have achieved so far, and this is important to acknowledge, is that we have written this inequality, the first one with the minimum, we have written it down without the minimum. So now the question is, since we cannot compute kappa 1 star, how can we use this inequality in practice? How can we determine VF and XF so that this inequality is satisfied, since we cannot really determine kappa 1 star? And here's the idea. The above condition holds if there is any control law kappa f, it doesn't need to be kappa 1, any other control law kappa f, such that the same inequality is satisfied, but with kappa f in lieu of kappa 1 star. So it doesn't have to be kappa 1 star. I'll leave this to you to see why it is so. I'll leave this to you to see this as an exercise. These two conditions are not equivalent, but if you can find some other kappa f, which can be something very simple, of course, since this is up to you to decide, you can take kappa f to be a very, very simple function. For example, a linear function. So if you can find, let's say, a linear function so that this inequality here is satisfied, then the original inequality is of course satisfied. This is an exercise. So now let me state the problem again. Find kappa f, find a simple kappa f, so that Vf is larger than or equal L of x, comma kappa f of x, plus Vf evaluated at f of x, comma kappa f of x, for all the values of x inside xf. And as we said before, xf is control invariant, and in fact here it is positively invariant for the system xt plus 1 is equal to f of xt, comma kappa f of xt. So if you use that controller, if you use that special controller that you came up with, then xf is positively invariant for the corresponding closed loop system. Why is it so? That's a good question, and it's a very good exercise. Now let's see how we can use what we just discussed to really determine kappa f, Vf, and then xf for our MPC. From now on, we will be assuming that the regularity assumptions hold, and of course that the attractivity assumptions hold as well. The problem statement goes as follows. We're trying to find Vf, xf, and kappa f, which is known as a terminal control law, kappa f, which is defined on xf, such that xf is positive invariant for the closed loop system with that terminal control law kappa f, and second, that Vf satisfies the following inequality, the same inequality as in the previous slide. I just rearranged it here so that it becomes evident that this inequality is precisely a Lyapunov decrease condition. That's exactly a Lyapunov decrease condition on xf, however. Okay, so this inequality must be satisfied just on xf. And if these conditions are satisfied according to the attractivity theorem that we stated in the previous lecture, the origin becomes globally attractive over xn for the MPC controlled system. This comes from the MPC attractivity theorem. Now let's take a more concrete example. Let's see how we can precisely apply it when the dynamics is linear. Suppose we have a linear dynamical system of the form xt plus 1 is axt plus but, and take x and u to be some simple sets. Let's say they are convex polytopes. Take the cost function to be a quadratic function, like this one, 1/2 x transpose qx plus u transpose ru, where q and r are symmetric, positive definite matrices. And choose the terminal controller to be something simple. Take the terminal controller, kappa f, to be just k times x, where k is as a constant matrix. Now choose k to be a stabilizing gain for the linear system. We assume, of course, here we haven't mentioned it, we haven't written it down, but we assume that a comma b must be a stabilizable pair. So assuming that it is, we can find again k, which stabilizes the linear system, and find a matrix P, which is given by q bar plus a bar transpose p a bar, where a bar is a plus bk and q bar is q plus k transpose rk. Now this equation you see here is a matrix equation. The unknown is the matrix P. This equation is known as a Lyapunov equation, and there are software that we can use to solve it. So don't worry about how you can solve it, so long as you have determined the stabilizing gain and you have Q and R and you know all the constants of the problem. You can very easily use some software to determine this matrix P. Once you have that P, let's move on. Define the terminal cost Vf, which is equal to 1/2 x transpose Px. So use that matrix P to define the terminal cost. So that's it. We have determined so far the terminal controller and the terminal cost. We now choose xf to be an invariant set for this linear system, for the linear system xt plus 1 is equal to a bar xt, where a bar is a plus bk, and we choose it to be an invariant set for this linear system, subject to the constraints that xf must be a subset of the given state constraints, xf must be a subset of x, and k times xf must be a subset of u. Now this last condition here means that if I take a state x inside the terminal set xf, then kx will be an admissible control action, will be a control action inside the set uppercase U. As an exercise, you can confirm that by choosing this exact terminal controller and this VF and this XF, then we satisfy the MPC stability conditions. Therefore, we have attractivity. And perhaps we might even have global asymptotic stability. We'll see about that. Now there is a better way to choose the terminal controller, there is a better way to choose the terminal cost, and a better way to choose the invariant set. So let's have a look. Choose now the terminal controller to be again of the same type, so kappa f of x is k times x, but use the infinite horizon linear quadratic optimal control problem to determine the gain k. So now k is the so-called LQR gain, the linear quadratic regulator gain. And how do we determine that matrix k? We determine it by solving the discrete time algebraic Riccati equation. And we get k from that equation, and we get p as well. So p now is the solution of there. P is given by q bar plus a bar transpose p a bar, the same as before. The only thing that changes is that k is the LQR gain. In fact, here we do things the other way, if you remember. First we solve for p, and then we determine k. So first p, then k. But this can be done using some software. And then once we determine that p, we define the terminal cost Vf, which is 1/2 x transpose px, same as before, and we choose xf to be now the largest possible invariant set. The word largest is in quotation marks because we haven't defined properly what largest means when we talk about sets, but we'll do that in a moment. So the largest invariant set for xt plus 1 is a bar xt, subject to the same constraints as before. So this is how we can determine, this is how we can design MPC controllers for linear systems with constraints. We have explained how we can construct the terminal cost function and how we can choose the terminal controller, the last thing that we need to determine is how we can choose, how we can design appropriate invariant sets. And this brings us to the next section, MPC for linear systems, determination of invariant sets. Now here we will study how we can determine invariant sets for simple linear systems like this one, xt plus 1 is equal to a bar times xt, subject to certain constraints. And the constraints we have here are that the state xt must belong to a certain set denoted by x subscript kappa f. What is that set? It's the set of all states x in x uppercase such that kx is inside u. So these are the constraints we stated before. So we're looking for a way to construct invariant sets for such linear systems subject to constraints. Let's give a definition. What did we mean before when we said we want the largest invariant set? Well, let's replace the word largest by a more appropriate one. Let's define the concept of a maximal invariant set. Maximal. The set O infinity, which must be a set inside x kappa f, is called a maximal invariant set for the above system if, first of all, it is an invariant set, it's a positive invariant set, and second, if for any other positive invariant set O, we have that the other set must be contained inside O infinity. So O infinity is like an all-encompassing set for all other positive invariant sets. You cannot find a larger one. In fact, if you find any invariant set, it will be inside O infinity. O infinity is the largest invariant set in that sense. Let's see now how we can compute such invariant sets. Suppose that A bar, the matrix A bar, is a stable matrix. Of course it is, because we chose K to be a stabilizing gain. This means that A plus BK is stable. Suppose that X kappa f is a compact set and that it contains the origin in its interior. Then the maximal invariant set O infinity can be computed by the following algorithm. So this is an algorithm, we can really make an implementation for it. Produce a sequence of sets O0, O1, O2 and so on, like that. O0 is x kappa f itself. And then Oj plus 1, the next set, is defined as all x's in x kappa f, such that the next state, A bar x, is inside the previous set. A bar x is inside Oj. We understand here that if this algorithm terminates at some point, if it happens that Oj is exactly equal to Oj plus 1, then we have reached a maximal invariant set. Oj is equal to Oj plus 1 means that this is an invariant set which is equal to O infinity. A few facts about this algorithm. The algorithm terminates, we say that it terminates when Oj is equal to Oj plus 1. The algorithm does terminate in a finite number of steps. We don't need to run it for infinite steps until it converges. Convergence happens after a certain finite number of steps. The third thing is that every time we execute the step of the algorithm, we obtain a smaller set or an equal set, in which case we terminate, but if not, we will be obtaining a smaller set. So Oj plus 1 is a subset of Oj. And the last one is that if x and u are polyhedral sets, then O infinity is also a polyhedron. Now let's see what are the exact computational steps we need to take to determine O infinity. Suppose that x is a polyhedron and u is another polyhedron, and x and u are characterized by a pair of a matrix and a vector, hx, bx, and for U, likewise, we have a matrix HU and a vector BU that characterize U. There are certain software to which you can pass these matrices H and the vectors B, and if we're talking about a two-dimensional or a three-dimensional polyhedron, you can get a plot of that and you can inspect it. In higher dimensions, of course, this is not possible. Now, x kappa f is defined as this set x belongs to x such that kx belongs to U. By substituting the above conditions for x and for U, and by rearranging and reorganizing the terms, we have that x kappa f is itself a polyhedron. You see, it is matrix times x less than or equal vector. Now suppose that OJ is a certain polyhedron, then OJ plus 1 is the set, by definition, the set of all x's in x kappa f, such that A bar x is inside OJ. And by using the above definitions, we can see that OJ plus 1 is indeed a polyhedron itself. So at every step, it becomes clear that we can construct a new polyhedron. And we only need to test when to, we need to have a mechanism to decide when to terminate the algorithm. Namely, we need to be able to check whether OJ is equal to OJ plus 1. So let's talk about termination. Once again, the algorithm terminates when the successive sets we will compute become equal to one another. But now look here, since at every step we are computing a set that is a subset of the previous one, it suffices to check whether OJ plus 1 is a superset of OJ. Let me say this once again. Under what conditions is a set, let's say A, equal to a set B? A is equal to B if and only if A is a subset of B and B is a subset of A. Right. Here we know that OJ plus 1 is always a subset of OJ. So it suffices to check the opposite inclusion, whether OJ plus 1 is a superset of OJ. And now the algorithm becomes initialize O0 with x kappa f and repeat OJ plus 1 is the set of all x's in x kappa f such that A bar x is included in the previous set. If OJ plus 1 is a superset of OJ, then return give OJ plus 1 which is equal to O infinity, and the algorithm terminates. We will not give a proof of the fact that the algorithm terminates in a finite number of steps. The question now that remains to be answered is how exactly computationally, how can we tell whether a given polyhedron is inside another? When can we, under what conditions a given polyhedron contains another? And we're looking for something that we can implement on a computer, and so we're looking for the exact steps, the exact computations. So let's have a look. The problem is stated as follows. Tell whether the polyhedron A1, which is given by all the x's such that h1x less than or equal b1, tell whether it is contained in A2, which is given similarly. H1 has S1 and S1 number of rows and n columns. H2 has S2 number of rows and n columns. Now let's have a look. A1 is a subset of A2 means that a point x is in A2 whenever it is in A1. A1 is inside A2, it means that all points of A1 are also in A2. What does it mean to be in A2? It means that h2x less than or equal b2, and this must be true for all x's in A1. So this means that every single element of the left-hand side of h2x must be less than or equal every corresponding element of the right-hand side. What are the elements of the left-hand side? So the ith element of h2 times x, it is the ith row of the matrix h2. We denote this by h2i transpose times x. So the ith row of h2 times x. This is the ith element of h2x. This must be less than or equal b2i, the ith element of b2. And now this must hold, of course, for all I and for all x, as we said before. Equivalently, we can write that h2i transpose x less than or equal b2i, the same exact thing, for all x that belong to a1. This means that for all x such that h1x less than or equal b1. And this must be satisfied for all I. Now, since we have an inequality that must hold for certain values of x, must hold for all x, then this is equivalently written as follows. The maximum of the left-hand side for all possible values of x in a1 must be less than or equal b2i. So instead of writing for all x, we can see what is the largest value that the left-hand side can take. Can it possibly be above b2i? So if the worst case, the largest value of the left-hand side for all x in a1 is below less than or equal b2i, then we're good. But this, of course, has to hold for all I. So checking whether, this is the result, but let's see how we can really use it in practice. Now, checking whether a1 is a subset of a2 amounts to solving S2 linear optimization problems. These are called sometimes linear programs. So if you want to check whether a1 is inside a2, you need to solve a bunch of linear programs. The good news is that there are plenty of software out there that can solve linear programs very, very efficiently. So it is not particularly computationally prohibitive to solve linear programs. In fact, for problems of reasonable size, this can be done in less than a second. And this condition now can be checked very easily computationally. Let's now have a look at an example. Take this linear system. xt plus 1 is a matrix times xt plus another matrix times ut. xt is two-dimensional, ut is one-dimensional. The system is subject to certain constraints. In fact, this system and these constraints are the exact same constraints and dynamics that we used in the previous video lecture. And in fact, we're using exactly the same stage cost. L of x and u is the norm of x squared plus u squared. We choose kappa f to be a linear controller, which is kx. K is the infinite horizon linear quadratic optimal control problem solution. It is the LQR solution, and we can determine k by solving the dare equation. And Vf is equal to 1/2, sorry, not without 1/2. Vf is x transpose px. We've just dropped the 1/2 from everywhere. Now, O infinity we see here is that green set, the set outlined, circumscribed by the green line. This is O infinity, which is of course a much larger set than what we had used in the previous lecture. So previously we had used just one point, the origin. Now O infinity is a quite large set comparatively. And the red set you see outside is the set of feasible states, the set of states that can be controlled by an MPC with horizon 2. You see, this is very large. So with horizon 2 we can control all these states. For comparison, had we used the origin as a terminal set, as we did before, then the set of states that we would be able to control would be the set circumscribed by the dashed yellow line. So compare the red set with a small set that is described by the dashed yellow line. Of course, the red one is significantly larger, and this is because of the fact that we use O infinity, the largest, the maximal invariant set for this problem and these constraints. Similarly, here we see the same for a horizon of 4. Of course, the sets increase in size. And for a horizon 6, we see that x6 becomes quite large. Now we fix the horizon of the problem equal to 6, and we start from a few of the extreme points of the set of feasible states, and we run a simulation and we see how nicely the system state converges to 0. Here we can see the same but in time. So we see x1, which is the green line, and x2, which is the pink line. They both start from a certain initial condition and converge to 0. We see that none of them violates the constraints. They touch the upper bound, which is 2. We have imposed that xt must be below 2 in both coordinates, and so it does, which is good. And we see that the control action is equal to -1 throughout the first few time instants, and then gradually it converges to 0. But neither xt or ut violate the constraints, which is very important. This plot shows the, let's say, energy of the system, the value function v6 star, which is both the value function of the optimal control problem and a Lyapunov function for the system, and we see how it drops and converges to 0. So now a few points that we should highlight. By choosing xf the way we did, by choosing xf to be O infinity, the maximal invariant set, and by choosing kappa f and vf the way we did, namely by solving the infinite horizon linear quadratic optimal control problem, as we did before, we have the following remarkable properties. First of all, xf equal to O infinity is very large. It's significantly larger compared to just 0. This leads to a larger set of feasible states. Second, inside xf, not everywhere, just inside xf, by solving the finite horizon optimal control problem, we obtain the same value function as if we would be able to solve the infinite horizon optimal control problem. This happens only inside xf. And another very important property, and this has practical implications, is that when we are inside xf, once we enter there, kappa n star is equal to kappa f. What does it mean? It may take time and computational effort to solve the finite horizon optimal control problem to compute kappa n star. But it so happens that inside xf this is equal to kappa f, and we can compute kappa f really very easily. What is kappa f? It is k times x. So inside xf, the MPC control law, the MPC control function kappa n star, becomes linear and becomes very simple. So we can flip a switch, and once we enter xf, we can switch to the local terminal control law. But be very careful here. This only happens if we choose xf to be the maximal invariant set, and if we choose kappa f and vf by solving there. Then some more comments. If we have a polytopic set xf, we may end up with a very large number of hyperplanes, a very large number of constraints in that set, and this may make the problem hard to solve computationally. We will not address this now, we'll address it in the next video lecture, but this is an interesting question. What can we do if XF is very, very complex? And lastly, the optimization problem we have to solve by following this procedure is what we call a quadratic problem. So we have a quadratic cost function, x transpose qx plus u transpose ru. We have some linear dynamics and polyhedral constraints. The good news is that there is a lot of software such as CVXPy in Python that we can use to solve such problems very, very easily and very efficiently. So thank you very much for watching, and take care.